So our next speaker is also with University of Idaho. Sarah, she'll be presenting on, I'm just going to read the title here, Evaluating the Influence of Past Experiences on Swimming Behavior and Passage Success in Adult Pacific Lamprey Using Experimental Flumes and Accelerometer Telemetry in 2018. And kind of the intent with this initially was to, we had a experimental flume design that we are looking at as an option for passing lamprey, and a portion of the study was to look at success of adult lamprey using this. Would they move from the bottom to the top? And then there was some other accelerometer work that they incorporated with this, and Sarah will be presenting on that. With that, Sarah.
Thank you. Okay. So just an outline of the 3 objectives I'm going to cover in the talk today. The first one was to evaluate the swimming performance of adult Pacific lamprey in a prototype flume designed to test the feasibility for application as a passage structure. And the second objective was to understand how these different exercise histories relate to passage success. And the third objective was a pilot study, and this was to evaluate the application of accelerometer biotelemetry to estimate the energy expenditure of fish during passage. So just a brief background. Previous research and now current research has shown that a very large percentage, approximately half, of upstream migrating Pacific lamprey fail to pass the dam. And this is also shown to be condition specific and changes in space and time. In response to this, lamprey passage structures, which take advantage of lamprey's natural climbing ability, have been implemented at areas in the dam where bottlenecks, milling behavior, and high turnaround rates are observed. And these structures are currently in place at Washington Shore, Cascade, and Bradford Islands. And these are just this is an image of the UMTJ LPS structures that Matt just gave a really good overview before this. And these are just situated upstream of the UMT and downstream of the count window at the Washington Shore Fishway. And so this brings me to the first objective. This was to evaluate the swimming performance of this prototype flume in the presence or absence of weir structures. And so we looked at the proportion of lampreys that successfully passed, as well as passage time, in relation to the presence or absence of weirs, which were semicircular rounded PVC pipes that were situated approximately 1 meter intervals along the length of a 20-foot wetted ramp that had a 10% slope. The sample size was 50 lampreys per treatment, and that was divided into 5 replicates each. And we had a downstream and upstream antenna that were used to record approach and finishing times. All lampreys that did not approach the downstream antenna were excluded from analysis, and only the time record from first passage was recorded for analysis as well. And these 2 images of the low-angled weired lamprey ramp show on the left is the ramp with the weir treatment, and on the right is the ramp without the weirs. And now I'm going to show you a video of lampreys ascending the ramp with absence of weirs. So it's a fisheye view, so it's the one on the left is looking downstream and the one on the right is looking upstream. And then he goes, and then stops. And then I have one more video after this, and this video is showing lampreys ascending the ramp with the weir treatment. And that's it. So what we found, what this graph is depicting is we have the treatments on the x-axis, so weirs, and then the treatment without weirs, and then on the y were the number of lampreys. and found that a total of 30 out of 37 lampreys successfully passed in the treatment with weirs, as compared to only 25 out of 39 lampreys passed in the treatment without weirs. And so it's somewhat, the difference was not significant, but it is trending towards more lampreys successfully passing in the treatment with weirs. And however, we did find a significant effect of time of passage according to the treatments. And so on the x-axis, we have the two treatments, and on the y is the square root of time. And found that passage time was significantly faster in the weir treatment, with a median time of 2 minutes in the weirs as compared to a median time of 13.5 minutes. And this was also first passage time, first recording. Oops, sorry. And so overall, we found that both designs are fairly effective for passage, but the treatment with the weird designs did pass more lampreys successfully, and they had significantly faster passage times. So some of the next steps that we can think about if this was to be implemented as a passage structure are designing rest box intervals, so how long between rest boxes, as well as adequate discharge. And from the results of this experiment, as well as the fact that it is a pretty low slope structure, the rest boxes probably could be pretty spaced out, and discharge operated well at a fairly low discharge. And so now I'm going to give you a little bit of background before describing my second objective. Matt did a great job of discussing the Washington Shore route, but one of the problems we have is lampreys bottlenecking and turning around behavior in certain routes. And so depending on the route they take, they're more or less successful. And the Washington Shore serpentine weir section is one of the areas that has one of the highest turnaround rates, still standing around approximately 30%. But the mechanism behind this turnaround rate isn't quite clear yet. So in the next few slides, I'm going to be discussing some of the hypotheses regarding why we're seeing this behavior. So overall, on a large multiple dam scale, it's shown that larger sized lamprey migrate further distances overall. And this is in relation to discharge, timing, and temperature as well. And additionally, at this large scale, there's a genetic marker that's associated with body size and migration distance. And another thing to consider is turnaround behavior that might be exhibiting because lamprey are experiencing hydraulic conditions in which they cannot pass. In other words, it's exceeding their swimming capabilities. In a study by Mesa et al., it found that the critical swimming speed of an average-sized lamprey was approximately 0.86 meters per second. And a study by Kirk et al. In 2016 that swam lamprey in an experimental flume that manipulated 3 levels of velocity. Let me try this red there. Right here, these are 3 levels of velocity, and then measured 3 vertical slot weir length treatments in response to the turbulence, in the response of a turbulence or a non-turbulence inducing wall. And we found that even in the highest velocity conditions and the largest vertical slot weir length, lampreys are fairly successful in passing. In fact, success rates are almost 100%. And this points to possibly another mechanism causing passage failure. Additionally, at this small scale, single weir challenge, he did not find any size effect on passage. But what he did find was that in the highest velocity conditions, with the turbulence-inducing wall present, attachment time was significantly increased compared to the other treatments. And this is possibly indicating that exhaustion may be occurring. And so what this slide is depicting is just an overview of the size effects that we see at the different scales. On a large multiple dam scale, I don't want to do that, okay. At the large multiple dam scale, we see that larger size lamprey are more successful in passing. But at the small single weir scale, there is no size effect. And under a different view, exhaustion threshold hypothesis, we see that we hypothesize that as exhaustion increases, the larger size lamprey will have a higher threshold to fatigue, and therefore may be more successful in passage. And this is what this cartoon here is depicting. As exercise and intensity increase, or by manipulating prior exercise histories, we see that passage success will be greater in fish that do not experience the same intensity and duration. So this brings me to the second objective, which is to understand how these different exercise histories relate to the probability of successful passage. So this is the experimental flume where the experiments took place. On the right here is a mesh-covered cage in which lampreys were swum for for exercise that did not allow attachment. So this mesh here is covered with probably 1,000 zip ties, I think, which took a lot because they really like to attach. It was very difficult. And this at a predetermined duration and velocity. Afterwards, they were released and into the flume, in which they had to swim through a 1-meter vertical slot weir section right here. And downstream antennas were placed, as well as upstream antennas, to record approach and finishing times. So this is just a schematic kind of showing the layout of the flume. The downstream end, we have the cage, which is right here. And then antennas placed just downstream and upstream of the vertical slot weir section, and then a third antenna with a FIKE system in place to record finishing. And this is just the experimental design and flow, showing the treatment that every lamprey experienced. All lampreys were tagged and allowed to recover, and then assigned to one of 5 treatments. Treatments consisted of a control in which no exercise took place, and then 2 levels of exercise duration, either 1 20-minute repetition or 2 by 20-minute repetitions divided by a 10-minute recovery interval. And this was further divided into 2 levels of exercise velocity, either 1 meter per second or 1.4 meters per second for each duration. And this was considered the pre-trial treatment, and all took place in the cage. After this, lampreys were released into the flume at a velocity of 2.2 meters per second and given 2 hours to successfully pass. And all of these trials were conducted at night, which means I learned the value of sleep during this time. So this is just showing the experimental design. Each of the 5 treatments had a sample size of 36 lampreys, which were divided into 6 replicates. And I additionally incorporated a randomized block structure, so 6 blocks throughout the course of the season to account for variation in run as well as temperature, and also looked at the average size of lampreys across the season and found that it didn't differ much, slightly smaller towards the very end. And each lamprey was measured for length, weight, girth, and dorsal distance and had a pit tag inserted. Additionally, a subset of individuals had a blood sample, a pre-trial blood sample taken looking at different metabolites and osmolality. And as Matt was discussing previously, with the outbreak of what was bronchiolitis, we assigned a value for symptoms of illness that included red mouth, white spotting, and cloudy eyes. And this is just an image depicting what that red blotching looks like on the oral disc of the lamprey that is an indicator for bronchiolitis. So now I'll discuss some of my preliminary results. In this picture here, I had a video system set up in the cage. This is a lamprey that was swimming in the cage. And so what this is showing is the number on the x-axis is the lampreys that successfully passed and that failed to pass, and on the y is the size. And we found that there was no size effect. So the size distribution is fairly similar between those that pass and those that failed to pass. And this is looking on the X, we have the 5 different treatments, the control, and then 1 times high velocity is 1 repetition, so 20 minutes at a high velocity, and 2 by 20 minutes at high velocity, etc. And this is showing of the fish that successfully passed, these were their size distributions, and as you can see, it differs somewhat, but you don't see smaller or larger fish necessarily passing in the higher velocity treatments. And this is showing the fish that successfully passed, and then they have the different treatments represented. And we found that in the low velocity, low repetition treatment and the low velocity, high repetition treatment, there was a significant difference. This is the exercise that they experienced. They experienced an exercise velocity of 1 meter per second with 1 20-minute interval, as opposed to 1 meter per second in a 40-minute interval, and found that this was significantly different, and which is indicating that as you increase exercise duration is resulting in decreased passage success. And this is the same graph as the previous one, and we've found a significant difference between the low velocity, low repetition treatment right here, and then as well as the high velocity lower repetition treatment, indicating that increased in exercise velocity also resulted in decreased passage success. And this was supposed to be removed. Okay, so this brings me to my conclusions. We did not observe a size effect at this scale, as we were previously thought might happen, but what we did find was that increased pretrial exercise velocity and duration resulted in lower passage success. And what this is indicating is that fatigue might be playing a role in the ability to successfully pass, which further indicates the need for the ability to quantify the energetic costs of various behaviors and activity levels that fish exhibit during passage, especially for that Washington Shore fishway. And next steps would be to look at the physiological status pre and post passage. So my next step I'm going to be doing is analyzing some of the physiological data that I got pre-trial. And so this brings me to the third objective. And this was the pilot study to evaluate the application of the accelerometer tags to estimate the energy expenditure for fish that are passing in the Washington Shore fishway. And so just a brief overview of the different tag specs. The tag has a 1.5 G sensor, which measures acceleration on a scale of 1 to 100, and it has a 5-second sampling interval, known as the burst interval, and during this 5-second interval, it will transmit a value representing the max force that was detected. And the tag on the right here, this is the accelerometer tag, and this is the standard radio tag that we used. And the accelerometer tag, as you can see, is quite a bit larger than the radio tag. It measures at 9 by 42 millimeters and is 6.8 grams. So we size selected for fish that with a girth of greater than 11 centimeters to accommodate this tag burden. And this graph is a bit complex, but what this is showing is the result of one accelerometer tag fish that I released into the experimental flume that I was discussing previously for the duration of 1 hour. And the fish was allowed to attach and not attach at various velocities, ranging from just under a meter per second to up to 2.4 meters per second during this time. And what we found was that when the fish was attached, excuse me, at low velocities, it exhibited a low Gs. So on the x-axis, we have Gs down here, and then on the y is frequency, between 0 and 0.25. But it also, when it exhibited burst movements that usually lasted in a duration from 1 to 2 seconds, the tag values were between 1.1 and the Gs were between 1.1 and 1.5. And what we did find was difficult to discern was the behavior when the fish was attached at high velocities or free swimming at low velocities. The Gs overlapped, so you couldn't just read from the tag and discern what behavior the fish was exhibiting. And what this figure is depicting is the same fish that was released at Washington Shore Fishway outside the AFEP that successfully passed the dam. So the fish was originally released on September 5th and successfully passed on September 17th. And this data set is a accumulation of all the activity data the fish exhibited while in the Washington Shore section during that time. And so what was very interesting about this was that it appeared to be the majority of the time the fish was attached at low velocity conditions based upon some of the findings from the data in the experimental flume, as values were between 0 and 0.25. But the fish also exhibited at intermittent periods burst movements. So we had values from between 1.1 and 1.5. But there was almost no values in this mid-range. So possibly indicating that the fish was either, either resting in these refuge areas and then bursting forward. And some of the fish that we released, we also noticed that they were exhibiting some turnaround behavior where they go up into the serpentine weir section, come back down, go up again, and come back down, which is pretty interesting to see. So overall, some conclusions from this is that with the accelerometer tag, we can identify burst movements. And we can also estimate the activity level of the fish when it's navigating through specific areas of fishways. And some of the preliminary results from the pilot study shows that these low-velocity refuge areas to recover from these anaerobic burst movements might be very important for overall passage success. And future directions for for the next research is to combine accelerometer data with respirometry, and from that to estimate the metabolic rate, and from that you can calculate overall energy expenditure that a fish that might be associated with costs of certain behaviors or movement patterns. And with that, I'd like to thank all the wonderful people that helped me this entire field season, the Corps and the Fish Ecology Research Lab. And with that, I can take any questions.
Yeah, we've got time for one question.
Thank you, Sarah. A methodological question in regards to your experimental weir test.
Mm-hmm.
Knowing that it takes almost a week for some of these fish to fight through the Washington Shore serpentine weirs, as Dr. Kiefer pointed out, and based on what you learned with your accelerometry data, what is your opinion of your 20-minute fatigue trials, 20 and 40-minute treatments of your fatigue trials? Do you think those are representative of what these fish might face, or would you perhaps increase or decrease those fatigue trials if you were to do it again?
That's a really good question. If I was to do it again, I would like to increase the exercise experience they have to create more fatigue. I think would be interesting to see if there's more of a partition, exactly where that breaking point is, where they can recover, and where they decide where it's difficult to recover, and then you might see more turnaround behavior.
So you don't think that you hit a critical maxima for any of those fish with the 40 minutes of swimming?
I think I did hit a point. Just in one step of velocity and one step of duration, we did see a marked decrease in passage success. But just to see the behavior, possibly if you were to increase those, increase the exercise. But I think overall what this points to is that having recovery areas is very key. Yeah.
All right, Sarah, thank you.
Yeah.